Okay, great. Welcome everyone. This is our first seminar for this semester. Today we have our guest joining from Europe. Let me introduce our guest. So we have Kenneth Hayfield joining from University of Edinburgh. So Kenneth is a reader, that's associate professor in American English. Is working on fast and often good machine translation. He coordinates the Bergamot project, adding local translation to Firefox, ran the Paracrawl project, and was friendly competition with ISI in a material program. He wrote KNLM to do large language models before they were cool. So let's welcome Kenneth Hayfield for our NL seminar talk. Thank you, Ken. So the stage is yours.
Hi, thanks. So I'm primarily going to talk about translating fast, and if there's time, we'll also talk about Paracrawl, which is dumpster diving on the web for training data. I saw these signs as a tourist in China, and as you know, we put them through our automatic analyzer to build a translation system. And then hopefully it's able to translate Chinese to English in this case and produce some translation. But as you know, in the Hall of Mental Cultivation, that we need more data than just photographs of Beijing tourist sites. That doesn't scale. So the Statue of the Unknown Bureaucrat in Iceland will help us translate, because we can harvest lots of bureaucratic data, like governments that have to translate for legal reasons, etc. But then the problem is, if you say the chair broke and you use a bureaucrat, it tells you la présidente in the sense of chairing a session and not a chair that one would sit on necessarily. So there's a domain adaptation issue. And that's why you might want to mine the web for translations to get a very broad coverage of domains, including all the interesting things that people might swear about when they're doing online dispute resolution, that sort of thing. And you can download Corpora for free from paracrawl.eu. And the other project is building this automatic analyzer to make it go faster. It's very fruit branded. So there used to be an acronym here, but it's just called Bergamot, and it does translation in Firefox, but also on your desktop. And the difference is it runs client side, and that's privacy preserving, because none of the text goes out and into some cloud that could then be mined or sold. And there have actually been data leaks from translate.com, which affected a number of companies, and even Google Translate once had a data leak in their translator console where they sent people the wrong parallel corpora. And that project is still in progress at browser.mt, and I'll primarily be talking about that one. So there is some synergy here. We take data from the web, feed it into building these fast translation systems. And we also take MT data, the tool from ISI, that's probably the reason I'm giving a talk here, and throw that in as well, get what's hopefully a good translation system, make it go very fast. And then because we have fast translation, we can use it in the pipeline to mine even more corpora from the web, for which we use the translation system sometimes. As I alluded to earlier, the main focus will be the fast translation. So that's what I'll talk about first. And I've brought a number of demos with me. You can go to translatelocally.com as well and install for Linux, Mac, and Windows. It's a application that it translates, in this case, to Spanish as I type, and you can see it generating, hopefully faster than a keystroke. There's not much parallelization you can do when translating one or two sentences, since it's sentence level parallelism, but this runs on my local CPU, which is also running Zoom. And you can see when I make errors, I can fix them and go back and edit everything. Or maybe I want to translate to German, and now I've got a German translation going. And all of this is available on a desktop app. I can also like grab some Wikipedia content if I want to, just because I'm aware a lot of people don't speak German or Spanish. I certainly don't. So it's a little confusing or hard to tell if it's a good translation. So let's find some random German here from today's Wikipedia article and just copy paste it in. You can see I've got this whole block of Wikipedia text, and just in the time that I was pasting it there was a bit of a flash, and then it had everything translated. So moving back, that was the first demo. Another cutesy thing is you can actually try this without installing any software or extension or whatever by going to mozilla.github.io/translate, and hopefully it will work. And I'll show you what that's like. So this is running inside the browser. It is slower. I'm not going to put a whole paragraph of Wikipedia in there. We'll get into why it's much slower when it's inside the browser. But this is actually a full machine translation system compiled to WebAssembly that downloads the translation model from the internet on demand when you click which language you want to translate. Here, have some Estonian on the CPU, no web service involved. Okay. Oh, actually, it's still updating that one. And then just for the duration of the talk, sorry, people watching on YouTube, I don't really want to have a site that anyone can go to any web page through and use my internet access. But I've put up a full web page translator that you can just go to at home, neural.mt/demo. I like short, concise URLs. So we have a completely unmodified Firefox, and this is kind of a Google Translate-like experience. This is server-based. The server behind it is translating the pages as you click through them. But the point is, I'm on Spanish Wikipedia, and I'm reading English coming out of here. There are a few eccentricities, like we haven't quite got these square brackets from Wikipedia when they're superscripts, they still get attached to the words. So dealing with HTML and translation is always a fun problem when you have a mess of stuff on the web. But I can click links. Maybe that was not the most PC thing to click, but I'm on Wikipedia. Again, this is all from Spanish Wikipedia, not English Wikipedia, but it's translated it on the fly for me. And you can change in the URL, just use the 2-character language codes for the languages we happen to speak, support, and then it will translate those for you. Sorry, Tim, it's 639-1 codes. And if you really want to try it on your own, it does require some compilation right now, and it's under heavy development, but we have a browser extension as well. So I'll show you what the browser extension version of this looks like. Here I am again in Spanish Wikipedia. I've loaded a Spanish speaking page. The browser has run LangID on it, and it's presented this option bar at the top here with a translate button. I click the translate button, and then you start seeing that the Spanish has turned into English, all running locally. It's actually not even the fastest setup. Some of it's running on top of WebAssembly when it does that. And now I have a mostly Spanish page that I can read, and there's some quality issues with the way this is done. It doesn't have enough context, but we're working on fixing the browser version. So going back to the presentation, here's all the URLs if you want to copy those down for the demos. Just remembering that the online translator I'll have to take down so people don't access random web pages through my internet connection. And I'm not big enough like Google to have someone watching on that. Speaking of cloud service providers, here's the cost if you want to pay a cloud provider to translate 1 million characters. This is the initial cost. I know there are volume discounts. Google will charge you less if you do a large amount with them, and probably so will the others. So the pricing is less clear because they say contact us often. But just to give some context here, if you set up a cloud server on, in this case, Oracle Cloud Pricing, using one of the efficient translation systems that we've got, the cost of just paying that full always on rate for a GPU or CPU is 0.1 cent per million characters. Of course, that's one of the systems. There's a whole variety of systems. So we'll get into a lot more of how fast each variant is. But that's the headline number, 0.1 cent versus $20 to translate 1 million characters. The other disclaimer is, of course, some of that $10 is going to pay the translation team to develop the systems and all of that. So it's marginal cost, not fixed costs that I'm talking about here. And there are obviously fixed costs. This is a 3 million euro grant, for example. So I ran an efficiency shared task in 2020 and 2021. This is building on a lot of work that other people did in WNGT, and Graham Neubig took it over at one point, and then I inherited it from him in some sense. And we wanted to get the community to make things go fast. And part of the problem is WMT, the quality task, encourages building ensembles of 20 systems to get one more piece of quality, but no one would ever deploy that in production. So the question is, can we get both quality and speed, or some other efficiency dimensions like amount of RAM consumption and disk? And in this case, we use GPU and CPU hardware. There's two conditions. One allows for batching. It's just do throughput as much as possible, and that reflects the case where we're translating a web page. And also, there's a whole line of work on non-autoregressive translation with incredibly weak baselines that claims it takes a second or something to translate a sentence with an autoregressive system, which is just not true. And they're ignoring the baselines that exist in the literature. So this was intended to both set the baselines and troll them. In fact, what ended up happening is none of them participated in the latency task, but we have a bunch of autoregressive systems with speed that is now in the literature that they should be citing. Remember that when you're reviewing for ACL. So somewhat corruptly, I run and participate in the evaluation. There were 3 competing teams, Huawei, Nutrans, and Tentrans, and we submitted in everything and did the most submissions. There's batching and latency, so one sentence at a time or all the sentences at a time, and then a few cases of, are you allowed to use a full CPU or just one core, that sort of thing. We also did a focused human evaluation. So I'm going to show you some automatic metric results, but for the select systems based on what participants felt would actually be competitive after seeing the automatic results, we did a focused human evaluation. A lot more details on that in the paper. For example, Nutrans didn't bother putting forward their 36 core CPU batch systems because they weren't competitive with ours, and then we didn't have any competitors, so what was the point of doing human evaluation? For this, we took 1 million sentences and shuffled them. It's actually parallel data from various sources, and on average, there were 20 words per sentence, and by that I mean WC-W, just a very simple count based on spaces, not anything tokenized. Participants could tokenize however they wanted. We used fast hardware for this evaluation. It was not focused on the consumer environment. This is like the good stuff, an A100 or an Ice Lake, which is quite recent from Intel. And you can see the specific machines. So in this, we're looking for fast systems, but also quality systems. And that depends on your use case where you fall in the exchange between these two, because it's a trade-off. So a hedge fund might want a really fast system and care less about quality because it's just being read by an automatic system and they really want that low latency for the trade, whereas a human evaluator is probably going to want more quality. And that's why we present a Pareto curve of just who was the best subject to that quality, or who had the highest quality subject to some amount of time. And here's the measurement of speed. So we're looking at how many words can you translate in a second. In the GPU setting, there's 3 participants. The staircase line is the Pareto frontier. It's showing the highest quality systems. And to be buzzword compliant, I'm using the Comet metric, higher is better. You can see the blog for blue and HERF for CHRF, depending on how you pronounce it. But we can do 150,000 or more than 150,000 words in a second on one GPU, one A100, which is quite a big one. And this sunglasses guy is indicating where an ideal system would be. Ideally, you would have perfect Comet, but and infinite speed, but that's the direction of a good system. And then with Nutrans, you can compromise some of the speed and get better, and Tentrans you shouldn't use according to this metric. Going a bit faster, with human evaluation, it's roughly consistent. There's fewer systems because we selected some of them, but you can see we have the highest quality from Edinburgh, which is my group, and then the lower quality domain with some fast systems. On the CPU, we didn't have much competition for single core batch. On all CPU cores, we beat Nutrans and no one bothered to do a human evaluation. So we can combine CPUs and GPUs for measuring latency. This is when you have one sentence at a time, drip fed, and then once you finish translating that, it gives you the next sentence. And there's a little command line wrapper that does that. And it turns out that GPUs are more cost effective in terms of how many million words you can translate per dollar. Actually, I'm confusing myself. This is batched throughput. So this is how many million words can you translate for a single dollar, which relates closely to dollars per million characters, which seems to be the metric by which cloud providers sell things. It's not quite the same metric, but you can imagine inverting this graph. And here the GPU is the most cost effective according to the prices charged by a cloud provider. for an A100 GPU versus an Ice Lake CPU. The CPU is less cost effective in this case. But if we go to latency and actually measure how fast can I turn around a sentence, one sentence, we can get down to 10 to 15 milliseconds. And what's interesting is the GPU has this line around 15 milliseconds. And then below that, the faster systems are actually on CPU. At some point, the systems are getting so small that it's not worth sending the compute to the GPU and doing all that kernel launch overhead. And it's better to just do all the math on the CPU. We also ran a human evaluation on latency, and largely the result is that there's this higher quality system from us, and then Huawei did a nice job on the lower latency. We also looked at disk size. I'm not going to bother with showing you Docker, but we try to compress models as much as possible, and this is useful for download and to some extent for memory consumption. And somewhat crazily, we got a model below 8 megabytes, or another one that's more reasonable, just over 128 megabytes. This is log scale on the model size, so keep that in mind. And Comet scores on the y-axis, but this is all of the submissions regardless of the platform. And Edinburgh dominated the entire Pareto frontier of smaller is better for model size, and largely the reason for that is we reached out to 4-bit quantization, which I'll talk a bit about later. So somewhat in an inverted talk structure, now that I've told you how awesome it supposedly is, how do we actually do all of this? And it's a bag of tricks. There's a whole bunch of things we do to make models smaller and faster. And I'm not going to go through all of these points, but I'll talk about some specific techniques like knowledge distillation, a bit about search, and then do a long rant about quantization and how to implement it on a CPU and GPU. So knowledge distillation, which some of you have probably heard of, you can train a model directly from the parallel data, or you can follow this teacher-student recipe whereby you train a large high-quality model. It might even be a multilingual model. Then you use that system to translate a whole bunch of sentences in the source language, and you have a student that learns to produce the teacher's translations. It never sees real translations. It never sees real target language. It learns to emulate the teacher, and there's some vague hand-wavy notion that the teacher finds a good way of doing things and simplifies the problem for the student. One way of putting this, which is not necessarily a great outcome, is it makes the vocabulary consistent rather than having variety in language. And because it's more consistent, there's less phenomena that it has to model. If there's a 51% case, then it can just follow that. That also has implications on gender bias. I do have a paper on that too, but it's too much for this talk. So you can see that online. But the student model, you can make it much smaller, and by that I mean like a single layer decoder, 6-layer encoder, much smaller feed-forward network, and it will perform better when it's trained on output from this teacher without too much loss in blue, but it runs a heck of a lot faster because it's small.
Sorry, what does the column, the GPU column mean?
Oh, sorry, that was time on a GPU to run on some arbitrary text.
And is the student trained on the, or the student trained on the 4 teacher or the 1 teacher?
4. So yes, there is a loss of quality, 0.6 blue, 0.8 blue. And one thing we're looking at is always ways to improve the recipe for teacher-student training. I'm glossing over some of the details, but we add source monolingual data that was not used for training anything in the teacher because we can, and it's just translated to the target by the teacher. There's also some effects that happen with translation ease and the translation direction when you do knowledge distillation. It seems to like translating in the same direction as it likes translating authentic source text. It doesn't like translating translation ease back to authentic source text when you do knowledge distillation. So there's a directionality component of the test set that matters as well, but I haven't put that into the slides. With plenty of things we can talk about later, John. So one thing that happens when you do knowledge distillation is the student gets a really sharp probability distribution. And that means while beam search normally helps a teacher, and there would be a strong quality loss if you went to beam size 1 for a teacher, when you do it for a student, that doesn't happen. And it gets a lot faster because it has to do less work. It doesn't have to consider simultaneous hypotheses and all of that, and therefore the GPU time goes down quite substantially without that much loss in quality. And the other thing is it's nice because we don't have to actually normalize the probability distribution anymore. There's no more competing hypotheses. You're just following the thing that has the highest score, and who cares if it's a probability because it's not being compared with anything else. Another very common trick that's almost essential to running on a CPU is shortlisting. So we take the old style fast text, thank you, Chris Dyer, run word alignments, and for each source token, we try to guess what the target tokens will be. And in practice, this is like the top 100 words in the vocabulary, plus each token gets to predict its top 100 words. Take the union of all of that across the batch you're translating even, and you have a smaller vocabulary. Then only bother executing the output matrix multiply on that smaller vocabulary. This does have some problems if there's a rare word form that it should have used, and then it tries to assemble it from the stuff that's in the shortlist. So one has to be quite careful about tuning the size of the shortlist, and empirically and actually in the latency test, we did a bad job at that. Another thing that Microsoft's working on is nearest neighbor vector. So you use this Feist library from Facebook and remove the bias terms, then essentially you're finding the highest dot product between vectors in order to figure out what the top scoring word is. And that's faster than brute force doing all of the matrix multiply to figure out what the top scoring dot product is. Another thing we do is simplify the decoder. So normally in a transformer model, when you're generating left to right, it attends to all of the previous states that it's generated before it during this generation process. So it attends to 1 before, then 2 before, then 3 before, and that's n squared work for the attention to go back and look at all of these things. And instead, what we do is we could follow Zhang et al. Biao Zhang and just average on the fly. And you can do that in O of n. So it's the average of the states that it's attending to, not individually weighting them each time. And in practice, there was no loss in blue. We can argue about more fancy metrics, and it went much faster on the GPU. I'm not going to cover it in more detail, but we've taken this a bit further. There's the simple recurrent unit, and then what we call the simplified simple recurrent unit, which has even less structure, and it's actually just a recurrent neural network running instead of a proper transformer in the decoder. So a transformer encoder and an RNN decoder. Let's talk about quantization. So we actually use 3 different data types depending on the setting. If we want GPUs to go fast, we tried to get 8-bit working with Cutlass and everything, but in practice, the FP16 path is currently faster. On a CPU, we definitely use 8-bit integers with just linear scaling. So there's a scaling factor for each tensor that determines how it's quantized, and it's linear fixed point quantization. When we compress for size, and you saw we're good at minimizing size, that's actually a 4-bit representation, and we use log scaling instead. 4-bit logs worked better than what we were able to find with 4-bit linear scaling. Annoyingly, though, despite being quite hardware friendly with log scaling, if you think about it, you're doing a matrix multiply in log format with 4 bits. So the multiply becomes an add. And then when you want to convert into normal space, you just do a bit shift, 1 less than the value in log, because you can use log base 2. And then once stuff is back in normal space, you just do your addition there and accumulate over the whole matrix multiply. So in principle, you could do hardware without a multiplier if you had 4-bit log representations, or 8-bit log representations for that matter. But unfortunately, no one's implemented this efficiently in hardware that I can get my hands on. So we only use it for size compression. The other subtlety is if you abuse the model by quantizing it to 4-bit log format and get a small model, and then decompress it and then put it in 8-bit format, that's really damaging. So actually, all of our results on getting things really small in terms of size, just use FP32 when we're doing the actual compute. And it would be nice to unify those if I could get my own hardware company to collaborate with on getting some hardware for that. But let's talk about Intel. I work with Intel, and we need to do consumer grade CPUs that people actually have under their desk. And there is a history of 8-bit instructions on Intel processors. So MAD UPS is the most widely deployed one. It's the oldest one. And what it does is it takes pairs of 8-bit integers that are signed and multiplies them as a dot product with a pair of unsigned 8-bit integers, produces that dot product and gives you a 16-bit integer back, which, by the way, could saturate pretty badly. So this is an annoying instruction because I wanted to multiply signed integers by signed integers. I know if we had ReLU or something, I could happily have, if I just take the max of 0 with the value, then I would have an unsigned integer and I'd be happy with that instruction. But in practice for our models, we've seen that leaky ReLU is better than ReLU, so we still have negative numbers. Then Intel said, hey, neural networks are cool. Let's do the vector neural network instruction. And that's on newer processors that generally are not found under people's desktops or on their laptops yet. You can definitely buy these machines. And that does a dot product 4 integers at a time. It solves some of that saturation problem because it's doing 4 8-bit integers at once, and even does some addition for you. So we have a code path that uses that. And then the latest and greatest from Intel that basically no one has a processor for yet, you can't buy them, is this AMX thing. And they've actually gone and implemented, here's a tile of 8-bit matrix, here's another tile of 8-bit matrix, multiply them, and they finally gave us signed times signed instructions. So there's all these different legacy levels on CPUs, and on top of that, Intel has been making the width wider. So you might have 128 bits of this problem, and that means you can take these, let's see, 128 is 2 to the 7, and then you have 8-bit integers packed into that. And you can do this in parallel on all of those with one instruction. Or you can do twice as many with 256, or even 4 times as many with 512. And of course, you want your routines to support that. So there's all this code we've written that has multiple separate assembly paths that figures out what CPU it's running on, and then which routine should it call. And actually, fun fact, the compilers make this quite difficult, and we've found several bugs in compilers through this process, which has resulted in some interesting code. It's a lot of C++ with intrinsics and macros, and you probably don't want to see it. So Intel has this ugly signed times unsigned thing. We want signed times signed. The duct tape solution to this that everyone seems to use is, well, if you add 128 to a signed 8-bit integer, it becomes a unsigned 8-bit integer, because then it ranges from 0 to 255. So what you do is take one of the matrices, add 128 to it, and then later you have to compensate for having done that. But if one of the matrices is constant, and conveniently neural network parameters tend to be at this point, we're not doing training, we're just doing inference, then you could actually fold the correction factor for this into the bias term. So you're not doing additional arithmetic, you've just added to the bias term to remove that. Another thing you could do is you could just ask it what the sign bits are and apply it, and manually prepare that one of them will be unsigned and the other one will be signed by taking the sign bits off of one of them. But that requires extra instructions. So the skew method is what people tend to use, though it incurs additional risk of saturation. And this is where the compiler people come by and say, our compiler should be able to just take a nice description of an 8-bit matrix multiply and make it run fast on any hardware. But because there's this saturation that you could actually exceed the size of a 16-bit integer using that Intel instruction, it means it would technically not be a correct answer for the compiler to use this 8-bit matrix multiply instruction, 8-bit multiply instruction, not matrix multiply instruction at all, because it produces results that are sometimes off from what they would be if you correctly multiplied the 8-bit integers. And this all means that one has to manually tell the compiler, yes, I want to call this assembly instruction, here's the routine that does it, and you can't actually write some nice for loops that would do all of this. ARM, I'm simplifying here, has mainly 2 useful instructions for this. They have an S dot that is kind of like VNNI described earlier, but it's nice in that it's a dot product of signed 8-bit integers. And then I guess they added unsigned times signed because enough people were writing code for Intel that they figured it was worth having that. The US dot, which is not the US Department of Transportation instruction, came up later. So now that we have this mess of things that I just confused you with and you can wake up again, how do we abstract over that if we wanted to have a low-level abstraction? And WebAssembly is trying to do this. They claim to be a portable assembly that will run nice on ARM and run nice on x86. And the way they do that is by taking the lowest common denominator of functionality. And because there are differences between ARM and x86 on how they implement 8-bit multiply, and technically they behave slightly differently in these corner cases of saturation, they just don't give you any 8-bit multiply instruction. You have to emulate it using a sequence of 3 to 4 instructions. I forget how many it is. So if you're trying to implement 8-bit matrix multiply purely in a web browser, you get incredibly poor speed. And I've put this table here. This is how fast our translation system runs with everything compiled to WebAssembly, and we just changed how the matrix multiply is done. Pure WebAssembly, 95 words per second. If we duct tape and just directly call that Intel instruction, much faster. And then if we throw out the WebAssembly loops around matrix multiply and let us do it directly, it gets even faster, and then you can use all these nice architecture specific tricks. We're also adding ARM support, but I don't have numbers for that right now.
Can I ask you a question? So for those who don't know WebAssembly, is it safe to assume WebAssembly is a JavaScript engine that runs in a browser?
WebAssembly is a JavaScript dialect, let's say, that has assembly-like instructions that the intention is the web browser will then compile them to actual instructions on the architecture that it runs on. And it will all happen inside of a web browser. And the primary application of WebAssembly right now is cryptocurrency miners from websites that are using your CPU to steal your electricity and give them cryptocurrency. There are a few other applications, but honestly, that's the most widespread application of it right now. I think it's a poor technical design, because really what they could have done is taken a Clang intermediate representation where you have the C stuff that hasn't been converted to assembly yet. And then the browser would do the final stage of compiling it into something that runs natively on its platform. Basically, it's the new, more standards friendly, buzzword compliant Java, if you prefer to think about that. Like people used to have Java applets inside of web browsers years ago. So when I sent you that Mozilla demo of running purely inside the web browser, and I didn't care which browser you were running on, and I told you it's slow, that's the 95 words per second.
Got it. Thank you.
And a fun story is actually, I was talking to Brave about this, another browser company, and Brendan Eich, who's the inventor of JavaScript, then joined the Slack channel, and I explained to him why WebAssembly was slow for our use case. This has not resulted in adding the instruction to WebAssembly that I would like, but there is an open issue and Google is pushing for it, but there's been no progress over the past 2 years. There is a separate W3C effort to standardize like a machine learning thing that would give us your computation graph, and we'll give you 8-bit multiply and all of that stuff. And then the browser would basically have an entire machine learning toolkit in it. The problem is the timeline for that being standardized is after my project ends. So I've talked to them, but it's not something I can use right now.
So these speedups, these require you to know the hardware you're on, right?
Yes, and if you think about being inside of a browser as an extension, the moment I'm an extension, I'm already on your computer enough that like browser fingerprinting is no longer an issue, right? The concern in WebAssembly is we don't want people fingerprinting the machines by what features the underlying hardware has. or put another way, across like a whole bunch of people working on ARM, I haven't really needed to work on ARM because there's a lot of people optimizing for that. And the work we've done on x86, specializing for every little bit of hardware, it's quite painful to be told, here's an abstraction layer that doesn't allow any of your fancy tricks and it makes things much slower.
So is it in general, can you not tell what hardware you're running on? Like that's not something that's exposed generally to an extension, is that correct?
And so it used to be the case that extensions were like DLL or SO files and just C++ code loaded into the browser, and that's how Flash worked. Then there was a change led by Chromium and followed by Firefox that they're called web extensions. So they have more privileges, but they're running on top of the browser, and they're trying to shoehorn us into being a web extension, which would then not have access to C++. And the negotiating point with Mozilla has now come to this, okay, we'll let you have some C++ code that's small and does matrix multiplies, and that's the most performance critical part. And that's where this table is coming from. From a product perspective, the plan, if you download the desktop app, is to drop a browser support thing in along with that download if you want to, and that would have native translation speed. There's obviously the security concerns around, I'm writing native C++ code that runs on your computer. What happens if someone generates a pathological input that then causes all the Marian stack to segfault in a way that compromises your security? So really, I get that point, and there are some solutions to this, like allow computation of untrusted bytecode supported by the Linux kernel, the sort of containers thing that a lot of people are doing. And then also preventing information disclosure by way of translating things slightly differently depending on the underlying hardware, but we haven't been worried about that yet. In principle, someone could figure out which processor you used due to slightly different rounding behavior if their JavaScript was monitoring that we injected translations in there. And then fingerprint what hardware you have. I guess the high level point I'd make is WebAssembly is not ready for fast machine learning. The web community is aware of this, and there's a standard that's going to have like more or less a machine learning kit that gets chucked into the browser and then would have native kernels sitting behind it. The fun part of that is a lot of the time you can tell what hardware you're running on by how the floating point numbers are rounded and the order in which they're done. So it's not clear how fast they'll be able to do multiplies if they have to be perfectly consistent across all hardware platforms. Fun problems with the web. So switching to native speed, and you will recall the numbers from the previous slide. I don't actually have the exact model of hardware that Mozilla ran that experiment on, but just keep in mind, we're talking about 95 to 560 words per second. And here's what happens when you run on a native hardware. And this is what you'll get out of Translate Locally if you insert enough text. So that it can parallelize and find sentences of similar lengths to put in batches and all of this. This is translating 1 million lines in a batch. Well, and it can decide what its batches are. And this is a variety of consumer hardware, a laptop I happen to have in 2012, that sort of thing. At the bottom, we also just included the cloud server with 48 cores. Give you a sense of speed there. So I think the native speed is quite okay for consumer hardware. I'm concerned about how viable a web extension is if it is constrained by WebAssembly going slow. All right, with that fun conclusion, how are we doing on time actually? Oh, we're close to the end. I think I will skip the dumpster diving bit other than to say that we have a lot of parallel data that you can download from paracrawl.eu. It was created using these fast translation systems to translate everything into English and then doing matching. There's a few other techniques for this. I know Facebook is using laser, but Paracrawl came from a translate everything and match method. And then I'll skip to largely the conclusion of the overall talk here that, ironically, I am mining the web for training data, which has some interesting privacy implications in order to make you a local translator that is private and runs efficiently on desktops, so you don't have to send text out to the web while gathering all this personal information and hopefully not terribly damaging people's privacy using public information from the web. We did have some work on how to filter out like email addresses and that sort of thing from the data before releasing it. And we have an anonymized version that's based on named entity recognition. So there's a whole trend of privacy, especially in the EU with the GDPR stuff. Even though we're no longer in the EU, unfortunately, we have a UK copy of that legislation. And that means a lot more obligations, and a lot of them go away if you can keep the text locally on a machine. And I know companies have confidentiality requirements and such that they won't use online translation systems as a result. And this is a way to reach those people. So with 4 more minutes, I suppose I should ask for questions.
I have a brief question. Sorry. Have you done an ablation study with the different techniques such as knowledge distillation and the shortlisting to determine like how impactful they are?
Yeah, I didn't do a good job of including that here, but let me see if I can get up the graph we had one year. Oh yeah, this is a just see if I can nope, not that one. So there we go. I think you can see it now. We've got, maybe I can zoom this in a bit more. Oops. Sorry, I'm it's being annoying about bringing up the paper. Let me see if I can.
Which paper is it? I can just.
It's our WMT 19.
Oh, I see it. Okay.
WNGT 19. There we go. Okay. This graph. We've got the baseline, and this is speed numbers on these bar charts, and then confusingly we have the blue score in black here along with each of them. So you can see the bar chart is getting better, and in the batch condition, which is in practice what we're using for throughput, or the latency condition in orange, And then while these are somewhat old results, like the simplified recurrent unit, and then you do the simplified simple recurrent unit, then we tied the embeddings for the 2 decoder layers, and that's nice for cache efficiency because instead of bouncing back and forth between 2 sets of parameters, it can reuse the same set of parameters over again, even though it has the same number of flops. It's faster for memory. Then in this year, it was FBGEM 8-bit integer operations, but 8-bit quantization you can see, and some more messing around with SIMD stuff.
Thank you.
There's in the subsequent papers, there's usually tables that we have of each of them and pluses, but this is the most graphically friendly.
Okay, so if anyone else have questions, please raise your hand or maybe unmute and ask. Maybe we have 1 or 2 more minutes left.
I have this question in chat. Can you hear me?
Yes, let me read the question. So what's your take or rant on non-autoregressive transformers? Do they help speed up translation in practice? This is a question from Avijit.
No, they don't. Or at least it's not proven. So my rant on non-autoregressive MT is, first off, given the latency numbers we had of 10 to 15 milliseconds, those are generally below all of the latency numbers reported in non-autoregressive papers. Now, you might argue we've done all this work on optimizing every layer of the stack, and they haven't. My counter argument to that is I'm pretty sure they have some grossly inefficient code in their autoregressive stuff. And the fact that you've simply gone to the side and evaded your grossly inefficient code does not mean you've discovered something that's better from a modeling perspective. The second point to make on that is they generally use WMT 14 English to German, which has so many flaws. One, it's not big anymore. And we tried to make for our efficiency shared task submission, Jindra Helko was working on a non-autoregressive system, and he couldn't get the quality up on larger data sets. Also, WMT 14 has the problem that everyone cheats at blue, or at least use of that data set is correlated with using non-standard tokenization, as well as messing with the hyphenation, which I don't approve of. And then these papers do not report what they did in terms of scoring. And they also cite other papers and just copy the blue scores from them as if they were comparable, when there's no evidence that they use the same tokenizer. There's no evidence that they use the same level of cheating at WMT 14. And also they had, there was actually an error in WMT 14's English to German test set. And no one ever says if they use the original version or the corrected version of that test set. Another thing is non-autoregressive systems are generally tested on GPUs. And why would I pay for an A100 GPU to do one sentence at a time slightly faster, even if it were slightly faster, when I can have one CPU core go faster than them? I can do 15 milliseconds on a single CPU core. Why am I paying for an entire A100 to do 20 or 30 milliseconds? So there's, in my opinion, a lack of rigor in the non-autoregressive papers. And we need to start rejecting their papers until they have rigorous experiments that actually show strong baselines. They often do knowledge distillation for their own model, but they don't do knowledge distillation for the autoregressive model. And so their gains are actually an autoregressive knowledge distillation probably also would have worked, but then you have to bother to optimize the parameters for that. Another thing is their baseline is like 6-layer encoder, 6-layer decoder. And yeah, that's going to be slow. But non-autoregressive MT, they got rid of the decoder and replaced it with something else. And that means they should optimize against the most efficient autoregressive decoder, not just a bad one that they picked out from a paper that was emphasizing quality. I think I have this rant somewhere in slide form if I can find it, but.
Just a follow-up question. So all these numbers you presented there, I assume they are using the 6 and 6, or is it different? 6 and 6 layers, I mean.
The older papers are using 6 and 6. I've seen a couple that bother to do 12.1, but no other optimizations. Like they still have a transformer decoder instead of a simplified simple recurrent unit, for example.
Got it.
And actually, I know none of them have that because they tend to all be implemented in PyTorch, and PyTorch doesn't have a simple recurrent unit or a simplified simple recurrent unit. They have, well, sorry, I should say FAIRSEEK doesn't have those, and it does have an averaged attention network, but as you can see from this, from what's on the slide currently, it is slower. I go in through my papers and might be able to find the WMT20 rant.
I think we are running out of time. So this should be the last question. Oops.
I just want to say I'm scared my paper is going to end up with you as a reviewer.
If you're working on autoregressive MT, you should be. Is there a question to that? I don't know where the recording of this talk will be.
Okay. So let's. Sorry, we are out of time. Maybe we should take the follow-up discussion in individual meetings. Let's thank Kenneth Hayfield for presenting this amazing talk and enlightening us with the possibilities of fast and efficient machine translation.
Sorry, I found the Go It All trash thing that I can trash him for while we were talking. So here's GTAO Gu's autoregressive baselines. Here's his non-autoregressive systems. And here's Marian beating him in prior work that was already published at the time. Well, in prior work that was published at the time in green, and then the next year in 2019, which was after his work, it got even worse for him. So you can't use those baselines. Sorry, carry on.
Okay, thank you. Okay, everyone, let's thank Kenneth Hayfield for this talk. We will continue one-on-one meetings. And see you all in the next session. Thank you, Ken, for this talk.
Cheers. Thanks for having me.